All right, so questions. I posted a reminder that your SLP uploads are due Monday morning by 11, I believe, is the time. So hopefully you've made lots of good progress on your service learning projects. And same drill as last time, right? Fill it out. Get rid of that second page of instructions, save it as a PDF,
The time
upload
is
it to Canvas.
11.
And if you
100
upload it
hours.
by 11 o'clock Monday morning, I will send them to the printers. So I'll give them to Izad. Izad will send them to the printers, and you'll have posters for the presentation week 10. Yeah, we're in week 8 right now. So next week's week 9, and then week 10. Tuesday, 3 to 5. And it should be in Canvas. No, week 11 would be finals week. And I won't be here because I have jury duty. Yay. So I'll find someone to proctor your exam. Probably just cancel the exam. I don't know. Yeah. No, I don't want to deny you. All right, questions on ODPs? Yes. Particular questions on ODPs? Yeah. Posted it last night, actually. Yeah. Oh, I got my wrong password. Yeah. Yeah, it's the second file input, so what he just said, right? Open a file, read in one line of input, and if that line is a valid integer, return that value as the function value, but also set the value of this status variable to a 1, indicating that the return value is valid. If you read the line from the file and it's not a valid integer, meaning scanf fails to convert it to an integer, return the value -1 from the function and set the status variable to 2. So you're setting a flag to tell the person whether or not they can use the return value. And you're returning the actual value if it converts, otherwise you're returning -1. So it's probably one extra line beyond ODP 217. 217, I said you could assume the number was always a valid integer. This one you actually want to check. So check the return value from scanf and set the status flag accordingly. So it's a couple of extra lines of code. Should be. And then I'll give you a break on ODPs after this until Monday, and Monday we'll come back with some more versions of this. But we're past the real sort of, this is the last real sort of like core heavy concepts that we're learning is dynamic programming. We'll talk about sorts and searches and heaps, and those probably won't be too unfamiliar to you. They'll be using things that we've already been using. Questions on PA4? PA4, I'm hoping, is mostly done for most people. Possibly not quite all of the deletion, but everything else should be pretty much nailed down at this point, because you only got a few days left. Good, okay. Well, let's talk about more dynamic programming. Okay. Mm-hmm. Yeah, but be careful of the case where you go left and there's nothing on the right of that, right? In that case, this is the largest node in the left subtree. So that becomes the root. It adopts the root's right child, and you don't have to change the left child. But it's a slightly different case from this. Right, where this would be the largest one, and so you'd adopt the root's right child, and this would become the new root, and then it would adopt the root's left child. All right, so let's talk about more dynamic programming. So our next problem is the problem of rod cutting. And here's the idea. You have a length of material, metal rod, and you can cut this into different sized pieces. So the rod has an integral length. Let's say it's 8 inches. So each of these marks is 1 inch. And you can cut this rod into whatever size pieces you want. And cutting it is free. You own the tool to do this. So you could cut this into 8 1-inch pieces, 2 4-inch pieces, a 3 and a 2 and a 3. You could leave it uncut as just a single 8-inch piece. You could do a 7-inch and a 1-inch. Totally up to you. And you're going to sell these pieces that you've cut. The tricky part is that different lengths of material are worth different amounts. And it's not just longer is more valuable because these are being used for different things. So we have a pricing schedule, which looks something like this. So for each possible length, we have the value of a rod of that length. And our prices, let's say, are 1, 5, 8, 9, 10, 17, 17, and 20. And for a particular problem, you're given this pricing table. And the question is, given that pricing table and an initial length of material, what's the optimal way to cut it up in order to get the maximum amount of money? And certainly cutting it into 8 1-inch pieces is not going to be very valuable. It's going to get you $8, right? And if we don't cut it at all, it's going to get us $20. So cutting it into 8 pieces doesn't make sense. And cutting it into a 7-inch piece makes no sense because a 6-inch piece is worth as much as a 7-inch piece. They're both worth $17. So we would probably prefer to cut it into a 6-inch piece and then do something with the extra 2 inches. But we'd like a way in general to figure out how to optimize the value of this. So what's the optimal way to cut up an 8-inch piece of material given this pricing table to maximize the value? 6 and 2. So how'd you do that? Okay.
Well, 7. Oh, okay. So basically, you could brute force it, but you basically find the largest value first,
Mm-hmm.
and then test. So you have basically a point system,
Mm-hmm.
and then when you find the largest value, and then see how many points it's worth.
Okay.
Test the next largest value, and then if you have points left, then you go to the largest amount of points.
Okay. So it's kind of a greedy algorithm. So it's interesting to note that if this is worth 3, you get a totally different solution. Your optimal solution there is to cut it into 8 1-inch pieces. You can find the value per length, but that's not going to end up always giving you the right solution. Yeah. And I don't think I have an example handy.
Yeah, because if you cut it into 6 pieces, then you wasted money.
Yeah, it may be that the most valuable cut leaves you with 1 inch of material, but if you had done a slightly less valuable cut but had 2 inches of material, the profit from those 2 inches will outweigh what you lost by doing something less than the optimal first cut.
So are we assuming we only have one rod?
You have 1 rod, and it's whatever length you're told, N, right, or 8 in this case, and you're cutting it up however many pieces you like.
I guess doesn't take into account supply and demand. Which
So,
has higher demand.
yeah, so this is a fixed pricing table. You're guaranteed these prices for these lengths. And cutting is free, so there's no penalty. And it turns out a greedy algorithm won't work in general.
Could you start on both ends with like 8 inches and 0, and then you can vary that to like 7 inches and 1, all the way down until you have the 2 most valuable pieces, and then flip that again on either half piece?
Something like that.
It's like, I can think of a
But-
forced way to do that.
But what if the optimal solution involves 5 pieces?
Well, every time you cut it down into 2 pieces, you do the same algorithm on every subpiece.
Okay, so we can start doing some kind of divide and conquer or some kind of dynamic programming, right? So we could brute force it, right? Brute force is pretty simple. We could do it with 8 nested loops, and most of our combinations would be invalid, but we could simply find all the ways to partition 8 into integers that add up to 8 and just find the maximum sum that we get.
Are we assuming 1 cut? Or
No, many cuts as you want.
Okay, so then the 8 or the 8 ones would not be the most optimal.
It's not?
1, 2, 3, 4 should be more optimal than that.
You don't have enough material to get 1, 2, 3, and 4. Yeah. So it's constrained in a number of directions. So, but let's do what you were suggesting. Let's look at subcases. So here's one way to approach this. Your first cut will be one of the following. So it could be at the 1 inch mark, or the 2 inch mark, or the 3 inch mark, 4, 5, 6, 7, or the 8 inch mark, which means we're not cutting it at all, right? So I'm thinking of this as number of inches from the left side. And our first cut's going to be somewhere in here, right? If we're not going to cut the rod at all, then we're going to pretend our first cut is at the 8 inch mark, which means we're not taking anything off the rod. So there's 8 possibilities for our first cut. The order in which we cut this makes no difference, right? We're just chopping it up and we're delivering a pile of pieces to someone.
Can we eliminate some, like, for example, for 2 and 4, you can see that 4 is less convenient than 2, so you just, like, not do 4 anytime.
Why is 4 less convenient than 2?
2 twos is 10.
Right. So we could do some pruning of the tree here, right? We could say we never really need to worry about 4, because if we can do 4, we could chop that into 2 twos. So we can definitely simplify this, right? That's basically pruning the search tree. But that's only in this case, and there may be things we could do in other cases. So let's stick with this idea of pruning and see how we can do this more systematically. So, right, same thing with 6 and 7. We never want to do a 7 inch piece because it's worth the same as a 6 inch.
I guess in that case, you could test if 2 values are worth the same amount, take the smaller one.
If 2 values are worth the same amount, take the smaller value. That's a good rule. If one value is divisible by another and that smaller one, right, goes in, then we could eliminate. So we could do some prime number theory in here too. All right, let's think about the first cut. First cut, 1, 2, 3, 4, 5, 6, 7, or 8 inches from the end. And let's look at those possibilities. So if you cut off a 1 inch piece to begin with, your value is equal to, let me go back to a 1. Your value will be equal to the value of a 1 inch piece plus whatever you can get from the remaining 7 inches of material. Right? So your maximum value will be 1 plus whatever the maximum value is you can get from 7 inches of rod. If you make a cut at the 2-inch mark, your max value is the value of that 2-inch piece, 5, plus whatever you can get from the remaining 6 inches of material. If your first cut is 5 inches, the maximum value you can get out is the value of that 5-inch piece, that's $10, plus whatever you can get out of the remaining 3 inches of material. All right, this is assuming once we cut our 5-inch piece, we're not going to cut that piece further. So if we wanted to write a function for this, it might look something like this. So MaxVal n, this is the maximum amount we can get from an n-inch piece. So let's loop for all possible first cuts from 1 to n. So this value equals, and let me put some labels on our pricing table. So let's call this v of I, where I is the length. So v is a function that gives us the value of a rod of length I. So the value from making a cut at I is the value of that rod plus MaxVal of n minus I. Because after we cut off that piece of material with length I, we have n minus I inches left, and MaxVal will tell us how much we can get from that piece of material by cutting it up optimally. We add the value of the I inch piece, that's the value we can get by starting off with a cut of I. So best equals 0 if this val is bigger than best, then best equals this val. And at the end of our loop, best will be the maximum value we can get. So it's a pretty simple recursive function. And it's solving the MaxVal problem on n by looking at solutions for values smaller than n, in particular n minus 1, n minus 2, and so on. So what's missing in our MaxVal function? Base case. Good. Always a base case, because we're going to keep calling it with smaller and smaller values of n. And there's a possibility, possibly not in here, that this is going to go negative. So let's just throw a simple base case in. If n is less than or equal to 0, return 0. The base case will probably take care of itself even without that, because we're recursing inside this loop. And if n is equal to 0, right, it's not going to loop at all. Good to be careful. Question?
So you're going through all of the numbers up to n,
Mm-hmm.
and then looking at all the numbers up to n minus 1?
You mean if we unroll the recursion?
That's what I'm thinking about, yeah.
So let's look at this for MaxVal of 8. So we're going to need to know, if we cut 1 inch, what we get out of a 7-inch piece, and a 6, and a 5, and a 2, and a 1. And to solve the problem for 7, we're going to need to know what we get out of a 6, and a 5, and a 4, and a 2, and a 1.
So I'm thinking is if you just, I guess you kind of do need a for loop there though. It only does unique things on the left, and it goes through all of them. But that wouldn't give you the best solution.
But if we cache our results, like we did with Fibonacci, right, we're going to be able to just march right down this leftmost branch and pop back up, and it's going to be order n. It's going to be extremely efficient.
Yeah, with system searching for a value like that would be really inefficient.
Yeah, yeah.
That could be longer than the test 3.
Yes. So this is another case of tail recursion, right? We're recursing at the bottom of the loop. So if we wanted to work upwards, we could say, what's the MaxVal of a 1-inch piece? Well, it's 1. MaxVal of a 2-inch piece, we have 2 possibilities. Cut it into a 1-inch piece, so it's the best of the following. Cut off a 1-inch piece first, which gives us 1 plus maximum value from 1, or just cut off a 2-inch piece, which gives us 5. So MaxVal of 2 is 5. MaxVal of 3 is going to be the best of the following 3 possibilities. Cut off a 1-inch piece and add the maximum value you get from the remaining 2. Cut off a 2-inch piece, which gives you 5, and add the maximum value of a 1-inch piece, or cut off a 3-inch piece and add the value of a 0-inch piece. And in this case, this is 6 and 6 and 8. So max value from a 3-inch piece is 8. And we can keep going, so it's going to be order n squared in terms of retrieval. But each of these MaxVals that we're going to need, we've already calculated. So if we do this from the bottom up, instead of starting with 8 and working our way down, we do this 8 times, and that gives us MaxVal 8. And if you want MaxVal 9, it's 1 more loop with no recursion. All right, so this brings us to knapsacks. And this is the basis of your final programming assignment, which is on Canvas, by the way, and which we'll talk about tomorrow. But it's also a group project, so be figuring out who you want to work with. But it's a maximum of 3 people per group, so if you really want to work with someone, talk to them like really quickly before somebody else does. All right, so PA5 is going to be a knapsack problem. Now, there's a lot of different knapsacks. Fractional knapsack, there's a 0-1 knapsack, there's the unlimited, there's probably an inverse hyperbolic knapsack problem somewhere. But the general setup is basically the same. Imagine that you have a bag with a certain capacity, and you're trying to figure out how to put things in this bag to maximize some function. So classic example, you win a 100,000th customer at Office Max. Right? And you're the grand prize winner. And so they give you a bag and they say, as our 1,000th customer, you can fill this bag with anything that you want and it's yours for free. Okay, so you can walk around the store, anything that you want, as long as it fits in the bag, you can put as much stuff in there and you get to keep it. And that's their promotion to you. So what would you put in your bag? You probably would not fill it up with pencils. Right? Because a big paper bag filled with pencils isn't really worth all that much. But you might fill it with 256 gigabyte flash drives, because those are fairly expensive. Or if they had, you know, a little gold dispenser in the back, you might fill it with powdered gold. Okay, so it depends on what the inventory of items is. But in general, these knapsack problems are about trying to fill a bag with certain constraints in order to maximize some function, typically the value of things contained in the bag. So here's a fractional problem. So you're the millionth customer at a Whole Foods store, and everything they sell is sold in bulk. So there's these big barrels with scoops, and you can scoop out however much stuff you want. And that's all they sell in this store. Okay, and these barrels are infinite. They're unlimited because it's a cool Whole Foods store. So they have 3 items available. So they have oatmeal. Yeah. So they have oatmeal, and they have, I don't know, they have walnuts, and they have raisins. All right, and let's say oatmeal costs $1 per pound, and walnuts cost $5 per pound, and raisins cost $3 per pound. And you're given a bag which can hold 10 pounds of stuff. So it's based on weight instead of volume. So you're allowed to get 10 pounds of any things that you want. It's yours for free. What would you fill your bag with to maximize the value of your bag? Fill it with walnuts. 10 pounds of walnuts, that's worth $50. Would not make sense to put a pound of oatmeal in with 9 pounds of walnuts, because oatmeal is not as valuable. Right? So you would fill it up with walnuts and you walk out of the store and you're done. Okay, now suppose that there's a limit to how much of these things are available. So this is the value, and this is the amount available. And let's say they have 5 pounds of walnuts and 2 pounds of raisins and 10 pounds of oatmeal. So now how would you fill your bag? 5 pounds of walnuts, 2 pounds of raisins, 3 pounds of oatmeal. How did you come up with that solution? Biggest number, right? Take as much of the most valuable item as possible. If your bag's filled, you're done. If your bag's not filled when this is exhausted, find the remaining most valuable item, fill your bag or exhaust this, move on to the next most valuable item, and so on. And that is guaranteed to give you an optimal solution. Okay, so this is an example of what's called a greedy algorithm. It's greedy in the sense that it tries to optimize the solution at each point along the way. So you've got an empty bag. The first thing you try to do is get as much value in that bag as possible. And you do that by filling it with as much of the most valuable item as you can. Okay, so we call that a greedy algorithm. And a greedy algorithm works perfectly for this fractional knapsack problem.
Why doesn't it work well with the rock?
Well, let me show you a different knapsack problem where a greedy algorithm does not work. Okay, and it comes down to the fact that your rod's being cut in integer lengths. And so we can make an integer version of the knapsack problem. And this is called the 0-1 knapsack problem. And we're going to stick with the unlimited version. So there's no shortage of supplies here. You can take as much of anything as you want. But 0-1 refers to the fact that you can't subdivide the thing that you're taking. So we're back in Office Max. You can't buy half a hard drive or half a flash drive. You either take a flash drive or you don't take it. And if you want 50 flash drives, you can take 50 flash drives, but you can't take 50.2 flash drives. Okay, so everything is integral, and that's the same setup as the rod cutting problem. All right, so we have a pricing table. So let's say weight and value, and what the item is. Okay, so your first item is a pencil, and this is worth $10, and it weighs a pound. This is not a realistic pencil. It's a really big one. Your second item is a pen, and that's worth $21, and that weighs 2 pounds. And your third item is a book, and that's worth $56, and it weighs 5 pounds. And your fourth item is a car, and that's worth $78, and it weighs 7 pounds. Bless you. All right, so you have a bag. And if your bag capacity is 7 pounds, you want to take the car. Okay, the car is worth $78. If you do a book and a pen, that's 7 pounds, that's only going to be $77. And if you start messing around with anything with the pencil, you're just going to get lower. Okay, so for 7 pounds, your bag capacity, you want to take the car. And this kind of makes sense if we look at value per pound. So divide your value by the weight. Pencil's worth $10 a pound. The pen is worth $10.50 a pound. The book is worth $11.20 a pound. And the car is worth $11.14 a pound. And our most valuable item is the book, right? It's over $11 a pound. But if we put a book into our bag, we get $56. We've only got 2 pounds left. We can either get $21 out of that, which gives us 77, or we could put in 2 pencils, which gives us 76. But by ignoring this most valuable item and going to one that's slightly less valuable, we can get $78 worth of stuff in our bag. So a greedy algorithm does not work for this, right? And the reason is that once you make a choice, you're cutting down potentially some of your other choices in ways that a greedy algorithm ignores. A greedy algorithm assumes that if we take as many raisins, as many walnuts as possible, when we've exhausted the supply of walnuts, we have not negatively impacted how many raisins we can take, right? Or how much oatmeal we can take. But here, because everything is integral, if we choose to take a book, it may limit what our other options are. And so the greedy approach doesn't work. And we can brute force this, but that's pretty expensive. It's just like rod cutting. It's all the different ways that you can add up 1, 2, 5, or 7 times integers to add up to whatever your capacity is. So let's find a general solution. So WI equals the weight of item I, and V of I equals the value of item I. So this is our pricing table. And our capacity is just N. And so let's write down what the maximum value is we can get from a bag with capacity n. So I'm going to make a MaxVal function. Find maximum value for bag with capacity n. And just like rod cutting, we can approach this in steps. Whatever our optimal solution is, it's going to involve putting at least one object into our bag. And the order in which we put these objects into the bag doesn't matter, right? Because it's just the total weight. So we can begin by saying, what's the first object we put into our bag? So let's do, I don't know, I equals number of items in inventory. So for example, we have W1, W2, all the way up to W big I, and their values are given by V1, V2, all the way up to V of big I. So I is the number of items we can choose from. So for each possible item in our inventory, if we were to put item I into our bag, what do we do? Well, we've got item I in our bag. It's worth V sub I. So we have at least this much value in our bag now, the value of that item that we just put in. But that item weighs something, and however much it weighs, that diminishes the capacity of our bag. If our bag holds 10 pounds and we put in an item that weighs 2 pounds, our bag can now only hold 8 more pounds. So our original value, our original capacity, minus the weight of this item I, that's the capacity of our new bag. And what's the most value that we can get by putting items into a bag with this capacity? What's the max value for a bag with this capacity? Max value for a bag with this capacity. Be lazy. What's the max value for a bag with this capacity? There you go. That's all we got to do. If we put item I in our bag, the value we can get, the max value we can get is the value of that item plus whatever the maximum value is we can put in the remaining capacity, which we can find by just calling our MaxVal function. And as long as these weights are positive, n minus that weight is going to be smaller than n, right? Which means when we recurse, we're going to be using smaller and smaller values of n, which means as long as we have a base case, this recursion will eventually exit. So if we pass in a weight that's a capacity that's 0 or less, let's just return 0. So that's our basic formula. The maximum value we can get for item I is the value of item I itself plus whatever the maximum value is we can get when we diminish our bag's capacity by the weight of I. Does that make sense?
I might be missing something. How do we know the weight of I if there are multiple items in it?
How do we know the weight of I?
Yeah, because we have n minus WI.
So we're just adding one item to our bag, right? So n is the capacity of our bag. which may already have 20 items in it, right? But for this particular instance of MaxVal, we're saying my bag can hold N pounds. What's the maximum value of stuff I can put in? And this loop is trying all the cases where we put exactly one item in, right? So we try putting in item 1, we get this much value, and now our bag is diminished by whatever the weight of item 1 is. So we iterate over this, and we need to record the maximum. And when we're done, we can just return the best weight that we found. We got one other case we need to worry about, though. What if this is our pricing table, and we're recursing down through MaxVal, and right now, let's say MaxVal, we're trying to compute MaxVal of 2.
You have to check and make sure you've got enough room for it.
You got to make sure that your item will actually fit in the bag. We're adding item I to our bag, but what if item I doesn't fit? So we got to check for that. So if weight of I is less than or equal to N, then we can do all of this funny business. Other than that, this works perfectly. So loop through all the items in your inventory one by one, take the value of that item, add the MaxVal from a bag whose capacity is diminished by the weight of that item, find the largest resulting value. That's the maximum value you can get from your original bag. And it's deeply recursive, just like all of this. So what does this look like? So let's stick with our original inventory, 1, 2, 5, 7, and let's find MaxVal of 20. Well, we're going to need to find, if we put item 1 in, we're going to need to find the MaxVal for a bag that can hold 19 pounds. If we put item 2 in, that weighs 2, we're going to need MaxVal of 18. If we put item 3, that weighs 5, we're going to need MaxVal of 15. If we put item 4, that weighs 7, we're going to need MaxVal of 13. So we're definitely going to want a cache. And to find 19, we're going to have to find 18 and 17 and 14 and 12. And in this case, again, we're going to see that we're marching down all the possibilities over here. But that's only happening because we have an item that weighs 1. Right? Now, if our weight table was something different, if we had, for example, 3 and 7 and 10 and 15, and we wanted to find our MaxVal for a bag of weight 100, we'd need to solve this for 97, 93, 90, and 85. And for 97, we need to solve it for 94 and 90 and 87 and 82. And for 93, we'd need to solve it for 90 and 86 and so on. And we're not necessarily finding MaxVal of 98 anywhere in here, or a MaxVal of 95. Right, so it's not as simple a setup as Fibonacci numbers, for example. So we can code this up, and again, we want to cache the results. So that when we do, if somewhere throughout this we calculate MaxVal 87, when we come to here, we don't have to recursively find that value again. We can just read it out of our cache. So this in the rod cutting problem, we're only talking about finding the actual maximum value. But what if we actually want the inventory, the solution to how many of each item we should have to get that maximum value? So you don't want to just know that your maximum value is $80. We want to know what particular set of items should we put into our bag to get that $80. And that's just, with just in quotation marks, a matter of some more housekeeping. It's just keeping track of what items you're putting into your bag at each of these steps. And so one way to code this is to have MaxVal return not just the maximum value, but also the complete inventory of items that give you this maximum value. And now, when we get back the inventory for how to get the maximum value out of this, we simply bump up the count of item I by 1. And now we know that we can get this value with that corresponding updated inventory. And as we loop through and we're recording our best value, we also need to record the corresponding inventory. And then when we're done, in addition to returning the best value, we want to return that inventory itself. So integers won't work anymore. You're going to want something like a structure, probably, that has an inventory along with the value of it. And you just need to carry that information around with you. And how do you store an inventory? Well, if you've got these items indexed already, we've got items 0, 1, 2, 3, 4, right? Your inventory can just be a simple array of integers. And each entry says how many of the ith item do you have in your solution. So it doesn't use anything that you're not already familiar with, but putting it together in the right way can be potentially tricky. So PA5 will be a group problem, and part of the reason it's a group problem is because this is a great problem to try to break up into pieces. And part of what you're going to be required to do in your submission is explain very clearly in comments in the beginning of your main program what each person in your group did on this project. And I'm not going to accept something like we all kind of worked on different parts equally. Okay? Before you start, while you're deciding who you want to work with, I want you to think about who's going to do what, which means thinking about what are the pieces of this that it makes sense to divide. You're going to need to read in an inventory from a file. You're going to need to do some error on that. You're going to need to figure out the bag capacity from command line arguments. You're going to need a way to go through this and figure out the max value. You're going to need a way to track the inventory that corresponds to the max value. Lots of pieces to this. Okay. It's alone, groups of 2, groups of 3, your choice. But if you're not doing it alone, I want you to think about how you're going to divide out these tasks. And it's okay if everybody works on all of it together, right? But I want at least your initial intentions of this person's responsible for this piece, that person's responsible for that piece. Okay, there's lots of little details here. So it's a really good problem to sort of try to break up. It's also a good excuse to get more comfortable with Git, because that's a nice way to do collaboration. Right? That's part of what it's for. So we'll talk about details of PA5 tomorrow. Bring final questions for PA4 tomorrow. Don't look for me Thursday night. Right? So bring questions to class. We can talk about the ODP if there's questions on that. And we'll talk about PA5.